I'll explain the language for the non-chemistry people here. Does anyone know what the half-life of Plutonium-238 is?
26 days.
Really? Wow, you guys have a very inflated view of the radioactivity things. Okay, Plutonium-238, right? By the way, for chemistry people who can explain, because actually I don't entirely understand. Why is there a number there? What does the 238 signify? The mass. So that means what? How many protons and neutrons together? Yeah, okay. Could tell I did chemistry. Are in the nucleus. Yeah, at least I know what that is. Okay, and I can pronounce it. This thing is radioactive. Okay, it became sort of famous because there's a lot of it, well, not a lot of it, relatively a lot of it, at the power plant at Fukushima that melted down. Okay, so there was some of this there, and this is the most dangerous stuff. We'll explain this in a second because it has a half-life of just 88 years. Okay, now before I give you some comparisons, right, you need to understand. Oh, it's not a long time. What is half-life? What is half-life? Okay. An excellent game is what it is. No, firstly, right, you want to think about this idea of decay, right? It's, some of you only just got it. We're really slow this morning, aren't we? Okay, fine, it's an old game. Half-life is the idea that when you've got some radioactive pile of material, okay, because it's radiating stuff off, okay, it's radiating out energy, okay? But even really dumb non-chemistry people know that energy and mass are interchangeable, right? So being that it's radiating out energy, it's actually losing mass from in there, okay? So after the passage of time, it'll become smaller. Still radiating out stuff, right? But it's radiating out less because it's already lost all of this mass, right? Now, half-life is a measure of how quickly that happens. The question is, given some initial amount, right, like say a kilo, how long would it take to get to 500 grams? Okay. Now the reason why it's called a half-life and not a 1 kilo to 500 grams life is because it doesn't matter how much you start with, as long as you get to half, right? So for instance, I could have just as easily have said 1 ton and 500 kilos. The reason why is because what we're looking at is always proportional to mass. So if there's more of it, it's shrinking down faster, okay? So this half-life of Plutonium-238 is 88 years. You're like, 88 years? That's forever. I'll be dead in 88 years or something like that, right? Just to give you a bit of scale, right? Other kinds of plutonium, is it isotopes? Is that the phrase? Yeah, other isotopes of plutonium. There's one, did I write it down? I did write it down. 234, or is it 244? It's 244. Okay, it's not 88 years, it's 80 million years, okay? So that's sort of more what we're talking about, right? It takes that amount of time. You know, you don't just walk along, you know, and you're like, oh look, there's a rock and it's disappearing before my eyes, okay? Things take a long time to radiate away, okay? And the reason why is because you need a heck of a lot of energy to lose any substantial amount of mass, right? But anyway, I'm getting into the science too much. There you go, there's a situation. The half-life of Plutonium-238 is 88 years. So here's the question I'd like to pose to you. How long will it take, if I did, suppose I did start with a kilo, okay? How long will it take to get from a kilo to 100 grams? Okay, how long will it take to get from 1 kilo of the stuff, passage of time, and then I'll only have 100 grams left? How long? And we'll just do it to the, let's just go the nearest year. Okay. Now, this question is kind of the opposite of this question, in that this held your hands like part A, part B, part C, and so on, okay? It really, really guided you through. Here, where do we even begin? I haven't even given you any variables, I've just given you some words. What should we start with? I want to form an equation. To form equations, I'll need some pronumerals, won't I? Because I don't know what any of them are. So let's introduce some. What do you think would be a good pronumeral to choose? We're talking about how heavy this stuff is, right? So how about M for mass? Right? Let M be the mass of Plutonium-238, okay? How much do you want to start with? How much Plutonium-238 do you want to start with? I know you could start with this, okay? But let's form a general equation first, because This doesn't tell you about, you know, I started with this much and then it ended with this much. It just says the half-life, okay? Oh, by the way, the traditional symbol for half-life is the Greek letter lambda, okay? I only like saying that because it's a cool letter. Now, if lambda is 88 years, okay, what equation can I form with this? Well, normally we would say, what does a decay situation look like? It looks something like this, right? So we're expecting something of this form. M equals m naught e to the minus kt, okay? Now, just off of here, right, I don't know what m naught is. M naught could be anything. Here's a specific example, okay? But I can still form an equation that tells me, like, from this, what kind of equation I'm going to be working with, okay? I should be able to still work out the value of k, how quickly or slowly this is happening. How am I going to do it? Where can I go from here, right? Well, if the half-life's 88 years, right, and I started with m naught, in 88 years, how much will I have? Half of m naught, right? Remember, m naught's a number. It's not changing like m. M naught's a thing that you start with, okay? So therefore, the mass will be half of m naught when the time is 88 years. Whoop, that's not a T, that's a K. There you go, okay? So you can see you can form an equation here that doesn't have anything to do with a particular mass, and that's the whole point of half-life, right? That it's irrespective of how much you actually have, okay? Right, so I can simplify this a little bit, can't I? I can get a half over here because I divided by m naught, and then you get to this point, and you will get to this point a lot, won't you? Okay. So again, I'm going to take logs of both sides. I'm going to swap the things around just to save myself a bit of time. Okay. So now I have a value for k. Just like before, we have a negative at the front that is not worth getting rid of. Okay. Even though you might think, oh, it'd be really cool and nice and neat to call this 188 log 2, because that's what it is. But this negative is going to cancel with this one in a second. Okay. So you might as well just kind of let it stay put. So now I can put this back in and say, well, therefore, this is what m is. Log, oops, 2t. There you go. So my negatives have cancelled out, but it is still a decay situation because that log half is actually a negative number. Right? Now I can put in my specific details here. And I'm running out a bit of room, so I'll stick in there. I want to start with a kilo, and I want to end with 100 grams, right? So where do those numbers fit? Which one's which? I want 100 grams, and I start with 1,000 grams, don't I? Okay. So I've got 100 over here, and 1,000 over there, right? And then I have all of this stuff up in the index. So now, just like before, I'll divide, I get this. I'll take logs of both sides to get that t out of power. Okay, and now all I need to do is divide to get t by itself, right? So if I divide, it looks like I'll get 88 of these over that. Okay? You can get your calculator out. Make sure you're careful with your brackets, and what do you get? Great. Now, again, does that make sense? Is that a plausible value? Does it look like what you expected? Is it in the ballpark? Being that you know 88 years is the half-life, right? And you're trying to get to 100 grams, a tenth of your size. After 88 years, you've got a half. After another 88 years, let's call that 90, because it's easier to do numbers in our head, okay? About 90 years, you've got half. Another 90 years, so 180, you'll have a quarter. Another 90 years, that's 270 years, I'll have an eighth. An eighth is pretty close to a tenth, isn't it? So we are in the right ballpark, and you can put it back in to make sure that it works with the equation. And there you go, okay? But as you can see, from about, let's see, from about this point, or possibly even earlier, all exponential growth and decay is just arithmetic. It's hardly even algebra, right? I mean, you've got the t floating around, but you just sort of push them around where you need to, okay? All of the tricky things are really in here in your setup. I hope you're getting the sense that often it's like that in these kinds of applications of calculus, okay?